to reach. Next, I'm bringing the post office box. Here what will happen, even if the resistance of order like this, 2.816, you can measure even this third decimal place exactly using this experiment. But such a thing is not possible in Wheatstone network, or such a thing is not possible in the meter bridge experiment. We can up to at the most maximum what happen, one decimal place as we can manage in the Wheatstone network or other things. But here what happen, we can even go for the fourth decimal also. So this will be to measure exact value, you know, this experiment is going to help us a lot. We can measure even the low resistance as well as high resistance. Very high resistance will go for thermocouple. We don't use even this one. Suppose if you want to measure something of order 1 mega ohm, 10 mega ohm, we go for thermocouple, because such a high resistance, your measurement will be a problem of order few ohms to few kilo ohms is what all these experiments what we are discussing. Very high resistance, I should go for thermocouple, or what you can say using thermoelectricity. If you look at the SCR mono, so one chapter itself is there. It's being removed. No longer now we are not using thermocouples. We are not using because they are very costly and lot of problems are there. So everything has become digitalized now. So we are not using even in applications nowadays. But to measure high resistance only, I'm going for that. Thermocouple. Okay, this is the post office. What is the advantage of this? We can measure even the fourth decimal also exactly using this experiment. So what this post office box, again, it works on the principle of Wheatstone network. It works, post office box, it works on principle of Wheatstone's network. You can see that R1 and R2, this is R1, this is R2. What are R1, R2? They're called as ratio arms. So R1 and R2, they are resistances. So these two are called as ratio arms. The unknown resistance is what this one. And it's a variable. This resistance will happen, I can vary this. This will be the variable one. And this we have galvanometer, and we do have two keys. This will be K2, this will be K1. And this is a cell. There is an electric circuit here. So by adjusting the value of R1, R2, so we can, these are called as ratio arms. So I am going to control the ratio of arms here. This X is unknown resistance which has to be determined. So the overall circuit will be like this. Then R is a resistance box. So here, what is that resistance box will appear like this. Are you seeing the plugs here? Are you seeing the plugs? Suppose I want 1000 ohm. I should remove this plug. Getting the idea? If I want that particular resistance, I should remove that plug. If I want, say like if I want to select it here, I think 20 ohm will be written. If I want to remove this, I should remove this plug. If you remove that plug, that resistance will get added up. So where is that plug? The plug will be connected in this gap. So it will be the knob will be like this. This will be a black color knob where you can unplug. When you remove that particular plug, then that resistance will get added up. The resistance what you find out by multimeter, the resistance what you find out by multimeter will have a error. Are you getting that one? Multimeter is not something, it will show error. Even digital multimeter here, it will show error. So even till date development to measure something resistive, I should come back to this old experiments only. There's no other way. Multimeter, okay, that one. Even 3 decimal places, but it will have error. You can see as you start using, the second or third decimal place will be fluctuating, will not be fixed value. You just take multimeter and check it. You can see exact picture. Okay, this is the there's a plug like this. So when you remove the thing, this one, so we'll get this one. So this particular plug, if you remove, no, it's like a key, and it'll be connected like this. The circuit in the resistance box, it'll be connected like this. This will be the one. This is what that. So when you remove that plug, that resistance will get added up. That we are showing in the form of symbolic form like this. Are you getting? So there's the one galvanometer is there. Again, what is the galvanometer? It should have the pointer. What is the condition for pointer? Even in the meter bridge everywhere, the pointer should be, the zero should be the middle of the scale. The zero should be the middle of the scale. So you write it 10 and 10. So I should use galvanometer where the zero should be the midpoint of scale. Everything in the Wheatstone network, in the meter bridge, potentiometer, I should pick up a galvanometer where the zero should be at the midpoint of the scale. This is a requirement. So this is about that galvanometer. I think, yeah, it is there, no? You can see 30, 30, not visible clearly, 30, 20, 10, 0. This is the galvanometer. Okay, this is a cell. It will appear like this. When you go to lab, no, the cell will be of this kind, where you can vary the EMF. You can control the other parameters. Okay, let's come for the overall that one. So now there's a circuit. So between A and D. So first we'll start with uh, here. This is a B, no. This is a point B. It is now between AB. So between AB, what you see the resistance. So what are the values you can pick up? If you remove this plug, 10 ohms will get added up to the circuit here. If you remove this plug, 100. If you remove these two plugs, 110. If you remove this plug, 1000. If you remove all these three, then how much will be? 1110 will be added to the branch AB. Same thing with this particular thing. This is a BC. Okay, got it? No? This is next the unknown resistance. So this would be unknown resistance. Here it is connected from C to D. The connection is made like this here. C to this particular D. And again, so I think the this D is missing. Let me add up. Okay, no, so there are two keys are there. One key will be there, and let's come for the galvanometer. So where the galvanometer is connected from the junction of these two ratio arms B to the D, no. So this you see that one. This is a galvanometer. A key will come, and that key what happen will pass through galvanometer, and that galvanometer will be connected to the point D. Try to see this. This will be. So there's a point B, galvanometer. That I'll show by dotted line. It will be internally connected. The key K2, then galvanometer. Here, if you want the key K2, you can bring it here. According to the circuit like this. First key K2, then galvanometer, and the galvanometer is connected to the point D. Okay, fine. And look at that unknown resistance. What is that R? R is what? The resistance that will added up in the branch AD, that one. The resistance that will be added up in the branch, the AD from here. So from here I can add up 1 ohm, 2 ohm. You can see all this particular thing will be added up. And this is the little bit wrong here. I'll make correction. This should be the cell. This should be the EMF, the cell, and this is the infinity. Infinity. So if you remove this plug, what will happen? Infinite resistance will be. If you remove that plug, here you become open circuit, infinite resistance, and this is the EMF. So where the cell is connected between point C and A, you can see the connection here. The cell is connected from point C. This will be the connection to the. This is a point A. Okay, the positive terminal. No? So I think here a little bit some. I'll make some C negative terminal should come. Some correction is there. First, let me remove all this. Almost, I think most of the books that they're given that nothing happens, only just I think you'll get confused here. This you call E, that one. Okay, I think now it will be okay. The negative terminal will be connected to C, and the key K1 you can assume it here. So it will be like a connected to key K1, then it will be passed. So this will be the key K1. I think I should have drawn this diagram. So many corrections are there. Yeah. Okay, fine. So key K1 either here or here doesn't matter. Sir. Either here or here doesn't matter. Key K2 here or this one. So this is about all the connections. Okay, why do, again, this is called like a ratio arms. So let's do one thing. Current to galvanometry is 0. Let's assume that one. So then according to the Wheatstone network, R1 by R2 is equal to R by X, and X is equal to R2 by R1 into R. So what is this R2 by R1? It becomes some ratio, no? So therefore, the AB, R1, AB and BC are called as ratio arms. I'm showing in the arrow that one. And this red color, this one, it shows that variable, and this is unknown. So by adjusting this R2, R1, I can control the decimal place. I can bring that accurate value. That's the thing. Fine. So now let's take the, so how that readings will take place, we'll go for it. Before that, there are two keys are there, no? So what to do with it, those two keys? Which key should be pressed first? So there's one more thing which some lot of things will happen. We have to take care here. So I'll go for the reading first, tabular column. Then I'll see that which key we have to. Tabular column. This is P, Q. I'll call them as ratio arms. So this is the resistance R. Direction of deflection, galvanometer. And this is unknown resistance X. Directly let me write the values so that it will be easy for you. Rather than just speaking theoretically, this will be, I'll make equal ratios, P and Q. So here the ratio ohms, I'll change it. R2 by R1. So this should be 10. Okay, 10. Yeah. This is, that will be R1. This is R2. The resistance of this will be 7 and 8. Lies between 7 and 8. Next thing, 2. I should reduce this ratio, no? So this should be, R1 should be 100, this will be 10. Then this will be 73, 74, right, left, lies between 7.38 and 7.4. Then I'll make this 1000, 10, 737. The deflection will be here nil. This will be 7.37. I'll show along with the value. It'll be very easy for you to understand, instead of just I'm speaking blindly. So what I do is like, oh, not responding screen. Okay, I think everything visible, what all I wrote. So let's begin with the working of this. So what I do, first I'll press the battery key. I'll give the reason in the end. First, press the battery key K1, and then the galvanometer key K2. This is something very, very important. Otherwise, what when an error will come. So why do that we have to do? In the end, I'll put it. So first, let's learn how to take the reading first. This one. So what I do, the first part, it will take, if you in the lab, no, it will take nearly half an hour. Sometimes it may take even up to 1 hour also to search the first reading. Once you get first reading, you can manage here. So first I'll assume the ratios R1, R2, 10, 10 ohm. So what I do, I'll remove 10 ohm in this arm, 10 ohm in this arm. Okay, got this. So here I'll just put a red color. So I removed it, these two. So 10 ohm got added up. So what is the ratios we made? 10 ohm. Then I don't know what I should start. So here I just put 7, 8. I don't know where the unknown resistance, what is the value of unknown resistance? Around 7.37. Then I can't make a guess, no, that the resistance which I want to find out will be 7. Or what you should have done, you should have done by using meter bridge or Wheatstone network, you should have roughly estimated what is the unknown resistance. Then you come back to then this experiment, so that the decimal place you can predict. If you want furthermore decimal place, no, you can go for ratios 10,000 by 10. Then one more decimal place will come, the third decimal place. So I just shown for only 2 decimal place here. So next year what happened? So what is the one thing is, first you do experiment by Wheatstone network, find out the value of unknown resistance, you get some approximate idea, then you can start experiment. When you don't know anything, so there'll be a real big headache. So what you're going to do, first you're going to press the battery key K1, then galvanometer key K2, then there should be some resistance. You should not start with 0. If there's 0 ohm, there'll be a lot of problem. So there should be some resistance. Then you start adjusting the value of R. As you start adjusting the value of R, the deflection will be like this. For this will be 0, no? The pointer, so what happen, will be on the right side. For what? For 7 ohm. I'm showing for R value when R is this much, 7 ohm. There's actually the meaning that one. So here next again, this 0, and the pointer what happened for 8 ohm, it will deflect. Don't write here 8, it will be like this. This will be the pointer. So this shows that the value lies between 7 and 8. Sir, how do I come to know? So what you should do is like, just pick up some, say 50 ohm. Let's assume that you have made 50 ohm. Then the pointer what happened will be somewhere far away here. Then if you make it 100 ohm, then it will further start deflecting, no? So as you increase the resistance, if the pointer, so initially for 50 ohm, so what actually happens in the lab is, say like this is 0. For 50 ohm, the pointer is here. Then if you make it 100 ohm, what will happen? The pointer will further deflect. So what does it mean? So somewhere we are moving away. So what I should do? I should decrease the resistance of value of R such that this is for R. When R is 100 ohm, when R is 50 ohm, if you, so 50 ohm, the pointer will be away from 0, it will be that one. If you make it 100 ohm, if it deflects further, what does it mean? Our answer is somewhere the less than 50, no? So shall I make it 150, 200, or shall I start decreasing less than 50? Lower than 50, I'll take it. So I'll come for 50. Then I'll make it 30. Then it will be like this. So like this, what happened? The first reading will be really some 30, 20. So finally 10, I'll come. And finally this, lucky. Okay, this is on the 8 ohm on this end. Oh, yeah, this will be like this. So finally what happened? For 8 ohm, I'll get it here. Now if I go for further, this one. So for 8 ohm, I'm somewhere here. Now if I make it 7 ohm, then I'm getting pointer on this side. So this shows that my reading is what now? The expected value is somewhere between 7 and 8. Then no sir, I'll start with 1 ohm. The 1 ohm what happened will be somewhere here for you. The 1 ohm will be somewhere here. The 2 ohm will be somewhere here. Got it idea no? So what we should do now? We should just pick up, sir, how do I come to know 50? You could have picked up even how much? 5,000 is there. So somewhere far away, the pointer will be from the 0. Then you decrease that value. As you start approaching 0 means definitely you have to go for further lower values. Then what you should do is like you have to search the two values which will be on either side of 0. 7 and 8 is what I got. This shows that the unknown distance lies somewhere between 7 and 8. But I don't know, is it 7.2, 7.3, 7.4. Got the idea, no? The first reading will take even half an hour also in the lab if you do it. Okay, next what I do is, after this what will happen? After getting that the deflection like this. So I'll do one thing. I'll make the R2 how much? R1, R2, R2 I'll keep it 10. R1 I'll make it as 10. This R1, this R2. So how much I'll make it R1? R1 I'll make it 100 and R2 as 10. So this will be how much now? 10 by 100, 1 by 10. Then the resistance value what happened? We expected somewhere between 7 and 8, no? So I'll directly increase this by 10 times. I'll directly increase by 10 times the value of R. Then I'll press first battery key K1, then galvanometric key K2. Then again I'll start searching. So here, so how the pointer, the readings will be, this will be 0, this will be 0. So when you pick up some say 70, 73 on the left side, no? Yeah, 70 will be like this. And somewhere 78 will be like this here, pointed. Then 72. This will be 75. So finally what happened? I'll see that 73 and I'll get 74. So you can start with 70. 70 to 80 is what you're going to move, no? Because you know expected value between 7 and 8, 10 times you multiply. So somewhere what happened? For 73, 74. Because I can't adjust 73.5. Not possible. You try to see that. We don't have that option. 73.5, can't make it. So therefore 73, 74. So somewhere the value lies between 73, 74. Then I'll substitute here. So 73 or 74. 73, this particular thing. 73 is there, no? This will by 10 you make it. How much will become 7.3? So this is only 7.3. Yeah? It should be. Okay, clear enough. So 7.3 and 7.4. The value lies between 7.3 and 7.4. So next what I do is like, I will make the ratio R1 is how much? Let it make 10,000. I'll remove this 1,000 plug. I'll remove this 1,000 plug. And R2 is as usual, 10 it is kept. Then what I do is like, I'll come for this. Then when I make it that 10 times I should increase the value of R. So 73, it lies between 73 and 74. So directly I'll start with 730. The scale I'll start with 730. 730 to 740 I'll take it. 73, 74, no, 740. This will be 0. This is for 730 ohm. So then the pointer, what happen, will be somewhere here. 730. Seven will come. This will be more should be on left side, no? 740. This is, sorry, 730. This will be 739. Here will be 735. Like this will be the pointer. What will happen exactly for certain value 737? It will show 0 deflection. Then, so what I'll do, so I know what is 737 is the value of R. So R2 by R1, 737 divided by 100. How much you'll get? 7.37. Like this, I'll obtain the exact value. If you want one more decimal place, make 10 by 10,000. Like this, you can predict even that third decimal place here. So there's a method of taking the readings. Okay, next after this, why the first the galvanometer, first the battery key, then galvanometer key. You know that like a inductance, capacitance, later chapters you are going to come across. Any shaped conductor will have a resistance, will agree. It's not that something cylindrical shaped conductor will have resistance. Any shaped conductor will have resistance. Similarly, any shaped conductor will have capacitance. Any shaped wire or any shaped conductor will have inductance. So definitely here we do have many things, no? Connecting wires. Here connecting wires are there. This open circuit, this keys itself what will offer some capacitance, will offer some resistance, will offer some inductance. So all together what along with the resistance, what we have, capacitor and inductor. And due to that what happen, they are energy storing elements. The first, when you press key K2, okay, no problem. No current, because this key K1, no current is there. The moment you press key K1, the current flowing will not be a constant DC current, will be a varying current. So how the current will flow? So what we expect, DC current constant value, no? But practically what happens when you switch on any circuit, DC circuit, it'll be off like this. Will be like this. And after some time, so what is this time? This will be depends upon usually around select 2 seconds, everything, even television, fan, any circuit you switch on, no? Here is what they will operate. This is the unwanted one. Here is what the equipment will get damaged. That's why you see all electronic and electrical equipments. When do they get damaged? Either when you switch on or switch off. Am I right? The maximum damage will occur for the equipments when we switch on or off. When you are switching off, switching on only. When you switch on, this is what happens. Even when you switch off, we expect it to suddenly current to become 0, but it will not happen. It will be like this. The curve will take like this. So here only the damage will occur. So switching off, very less. 10% of equipment will get damaged during switching off, but switching on, maximum 90% of equipments. Got this? So this particular thing here is what the circuit what will behave like a RLC, not only resistance, inductance, capacitance. And what is a galvanometer? Again, galvanometer what inside a coil will be there. And what is this coil? Will have inductance. Getting this one? So definitely when you switch on first K2, then K1, then because of that what like a current, varying current will flow. Due to varying current what some energy will get stored in the galvanometer. Some energy will get stored in the joints, where all joints, everything. Then again, as you start taking reading, no, that energy which was there initially when you switched on, no, that initial energy what happen will change the readings, and due to that error will come. So in the books what happen, they just use the word to avoid inductive effects. First the cell key K1, then K2 should be switched on. So why I'm doing this one? If I switch on first, if I close first cell key K1, yes, a transient current will flow, a varying current. Okay, got this? And since K2 is open, no current will pass through here, no? And the galvanometer will protect it from the varying current. And know that static energy will not be stored. Magnetic or capacitive energy, electrostatic energy will not be stored. Okay, fine. The galvanometer is what very important, no? Because even the deflection very nearer, it matters. You can see the way we are taking deflections, no? Something very, very important, no? The deflection. So that initial energy is stored, electrostatic and magnetic energy is stored in the galvanometer. So what happen, that will change this deflection with the time. So to avoid that inductive kick or so for that purpose, what we do, first I'll close the battery key K1. When I close the battery key K1, a varying current will flow through the circuit, but it will not flow through galvanometer. If a varying current flows, then only energy will be stored, especially maximum magnetic energy it is. Then what happens, once the current gets stabilized, a steady current flows. Then if I press K2, then what happens, a constant current will be flowing, not a varying current. So whenever a varying current flows, then what happens, the coil starts acquiring the magnetic energy. That magnetic energy will show error in the deflection of pointer. The magnetic energy also will get added up for the deflection of pointer, that one. So for that purpose, so when first I should press battery K1, then K2. So what are the reason we can give? What is the reason we should give for this? Any specific reason I should give for this? To avoid to avoid to avoid transient currents. So that's the main reason, to avoid transient currents. What these transient currents will do? They will, what happen, the transient, what all that current is, it will not like a decay immediately. Gradually it will decay. So therefore, this transient current what happen will store energy. Because of this transient currents, what happen? The deflection will be some error. So or in the books what happen, to avoid, the book they given like this, to avoid inductive kick. In the galvanometer, I think you will never understand this word kick. So it's better to go for scientifically. This just only in terms of language. The inductive kick means gradually the energy stored in the inductor open, that will also, energy stored in the coil also, due to that also some current will flow along with the DC current. That's what we just call to avoid inductive kick in the galvanometer. So therefore, what is the rule? First battery key, then galvanometer key. Okay, got it. I think it's around 8:20. Yeah? I took a lot of time. So we'll stop the class here. Okay, any doubt you can clarify? Post office box, it is earlier used in the application of telegram. Telegram, can you remember telegraph? I think now you might have not seen. I have seen before this mobile or telephone, if any urgent messages, then what happened? We used to print it. Please start early journey. Okay, that we used to transmit. And there what happened? We were using this particular equipment. And the telegram or telegraph, this particular post office, this particular equipment was very much important. That's why, since it was used in post office, no, so post office box, not like it's red in color. So now we don't use telegram, it's over. But still, I use this post office box to measure resistance effectively. Up to third decimal place, even fourth decimal place, we can measure accurately. Any doubt you can clarify? Any doubt you can clarify? What do you mean by instrumental error? That will be taken care, no? That will be taken care. Say due to flow of current. See, there'll be random error. There'll be random error. But the random error effect will be so minimum. That's why what happened, I'll take average. I didn't do uh, the the averages, that one. I just shown that one. So here what I'll do is I'll repeat this 7, I'll repeat this experiment 5, 6, 7 times for the same R1, R2, no? I'll measure this one. Then I'll take average. So like that, what happen, we can minimize the random error. Random error will be there. It's a part of things. Don't think that